Okay? And we're going to be doing a bit of jumping around, just so you know. This one slide covers everything that I would argue you need to have for spectroscopy memorized. Everything on there. The back of your head, so that when you look at a spectra on mass spec and you see an M+2 and it's 1-to-1, you know bromine's present. Well, what the hell does any of that mean? This is just notes. Right? You have to know what those things mean and what those things look like to use this. It isn't just memorize and you're done with it. But you need this content kind of at the back of your tongue so that when you see questions in exam 2, you can answer these in seconds. Right? And you can move on into the more detail-oriented questions that we will see. Okay? Is there a question?
So I was just watching this part video.
Yes.
That range, what are the units for it? Like, what are we
Good
looking at?
question. The units when we're looking at NMR are ppms.
ppm? Okay.
Yep. And yeah, you should never have a scale without units, so thanks for pointing out my lack of perfection. I appreciate that. Okay. Yeah, you know, at least we're all on the same page. What'd you get on the exam again? No, sorry. Yeah, I wouldn't do that. Don't answer that question. Also posted online, you see this file. This is what I call the spect.org file. The whole point of this file is just to organize all of your spectroscopy. Okay, so as far as the lecture goes, I posted something up there that said complete problems. The lab is forced to go through and do that. If you're not in the lab, you should also do it. Okay? You just won't get points for it. Sorry. Okay? But you should be doing it so that you know how to solve each of these spectra. This is my recommendation on how you put it together. Okay? On how you would go through and entirely solve something. Okay? Each of those is information about your structure. Okay? And the way we should kind of think about this is if you've ever put together a puzzle, that's spectroscopy. Okay? Except instead of putting it together as a puzzle, I gave you a bunch of pieces and I tore up all of the pieces and then I said put it together. Your job is to go through and assemble all of the pieces from spectroscopy so that now you have all of these pieces that you can now finally assemble into a final structure. Spectroscopy is a puzzle within a puzzle. Okay? If you like puzzles, spectroscopy is your gig. You don't like puzzles, welcome to the next rough 3 weeks of your life. Okay? And potentially more, depending. Okay? So it's a question of just putting together and assembling those pieces. Okay? The videos that I've got linked out, I know they're long, they're painful. They're 70 minutes that'll probably take you 3 or 4 hours to get through because of the amount of content jammed into them. Okay? Those videos really summarize one section out of the textbook. Not chapter, section out of the textbook. Okay? All textbooks are really good at going into the general theory and breaking down the individual concepts of spectroscopy. They are horrible at actually assembling a structure. So students at the end of reading sections on spectroscopy, great, they understand theory, they can't for the life of them solve a single question with spectroscopy because they don't know how to put it together. Our book actually has a chapter or a section within the chapter, 16.15, that is this. Okay? So shockingly close to what I'm showing you up here, you would think that I copied the textbook. I came first. Okay? Cardi came later. Okay? We actually had a conversation about it. Okay? He made it look a hell of a lot prettier, admittedly. Okay? But this process is what he's put in that section. How do you organize your thoughts? Okay? And for those of you who think that that organization isn't that big of a deal, that's how people get PhDs, is literally proving they're organized. Okay? That is the root of all science, is documentation. You can't document, you're not a scientist. Okay? And if we push this even further, 152 was all about documentation and the organization of how you solved. That is why in 152, the one word that should jump out of your mind, or maybe two words, depending on how you want to say it, ice tables. There is literally no reason for an ice table except organization. That's it. These are organic chemistry's ice tables. Okay? Ice tables were at least simple, just 3 lines, 4 columns, whatever. My tables can expand to be tens of columns and rows. Or not columns, but tens of rows. Okay? However many is necessary to analyze the spectra. Okay? Which gets us kind of to the next question, except we've got a guest coming in through the back. That was a lie. 5 seconds. Write down what you see. Okay, that was 5 seconds. You should actually have an answer. What do you have? Yeah, see that pause means you need a lot more practice. And I understand. It's okay. Okay? CHSP3s. We probably have an OH. Okay? We probably have a carbon-carbon double bond. We probably don't have a carbon-oxygen double bond because that would show up at 1700. Notice that little mark that I dropped down there? There's our 1700. This peak is a little bit under that, and the combination of that with that is probably moving more towards the carbon-carbon double bond from an aromatic structure. Okay? That's how fast it should be. Am I right? I don't care, actually, with IR. Okay? What I want is some simple bond information that I can then potentially use further on down the road. Okay? Yep, we have an OH. Yes, we have CHSP3s. Yes, we have the carbon-carbon aromatic. Damn, I missed the carbonyl. You were right. That was getting darn close to the 1700. It slid a little bit lower. It's not quite inside the range for a carbonyl. Why would it slide lower? An organic chemist's favorite 9-letter word, or an organic student's least favorite. Resonance. Your short one. Resonance. Resonance weakens the pi bond. As the bond gets weaker, what happens to it? It shifts to a lower frequency. Really? Yes, this is one of the things the textbook tells you. Okay? That doesn't necessarily help you in the solve. Okay? But what we're doing is drawing attention to this so that we can then potentially process further on. Okay? So you got the idea, right? We don't need another example? Too bad. 5 seconds. I'll give you 10 seconds. Mass spec's a little harder. That was 10 seconds. For those of us counting. What do we get? We got our M plus showing up at 93. Did I count that right? Yeah, 93. What does that mean? This is the molecular weight of the compound. It's 93. Anybody else get anything else? There's no M plus 2, which means no bromine, no chlorine. It's under 126. No iodine. It's odd, so we have at least one nitrogen. It's really rude to throw in multiple nitrogens, just for the record. Okay? It does happen. Okay? But usually if you're seeing an odd molecular weight, it's nitrogen. If you're seeing even, there isn't nitrogen. Okay? If there's 2 nitrogens, the 2 odds become even and it would mess with it. Okay? You should have that in 10 seconds. Okay? Can you get more? Probably. Good answer. Yeah. I know the total weight is 93. Do I know the mass of nitrogen? Mass of nitrogen is 14. If I only have one, I can do the math. I can't do the math. 79. Okay? Because this is organic chemistry, what other elements are likely in this compound? Carbon and hydrogen. So I could have 1 nitrogen and 79 hydrogens.
No.
No, that doesn't make any sense. So we'll skip the hydrogens and we'll go straight to the carbon. How many carbons could fit into 79? How would I do that? I divide by 12. I'm setting it up to do longhand like I would do that. 6 point something? 5, 8. Okay, which means I've got 6 carbons. C6. I have a nitrogen. And I'd have a hydrogen. 6 times 12 is 72. Which means unaccounted mass, I have 7. I could do that one. I have a potential molecular formula. That I don't expect to happen in 10 seconds. That requires a bunch of extra calculations. But all that is just math from Gen Chem. Like, you aren't doing anything fancy there. Okay? But recognizing that you have the ability to do that is the hard part. Okay? You have that ability. It takes practice to build it. Okay, get it? So like 10 seconds, we're cranking tons of information out. Make sense? We definitely don't need more examples. Another 10 seconds.
So this is massive iodine.
In 10 seconds, you can thank Raf later. What'd you get?
6 unique.
Okay. Good. I almost always skip that one. 6 unique carbons. How do you know that? Count the number of peaks. There's 6 peaks. This one's an alkane. These are all carbon-carbon double bond or aromatic. Really? Yeah. That's what you should be getting. Okay? That fast. And that one's done. See, that's not bad. That's kind of like IR. That was actually like 10 seconds. We definitely don't need to do like another 10 seconds. I'm seeing lots of pencil strokes, furious writing as you go through an attempt to solve these things. Okay? Yes, this will be a quiz. And yes, I will test you on this. You need to be working and practicing this so that by Monday, when I ask for 10 seconds, you can actually give me something. Okay? If you're one of those people that are like, I don't have anything yet. I know. You had a long weekend. You probably wanted to take a vacation. Sorry. Okay? We don't really get a vacation for 16 weeks. At this point, if you feel a little better, it's not 16 weeks anymore. It's only like 10. Okay, so that's a little better. You don't get a vacation. And one of those is spring break, where you don't even have to interact with me. You still have to do work. Okay? And during spring break, what I would recommend you do is start reviewing the old stuff before I cram more stuff on top of you. Okay? So when we go through and look at this, what do we get? Okay. HNMR is not a 10-second solve. HNMR is by far the longest of all of these, and you're probably pushing more towards 5 minutes to go through and do a full solve on an HNMR. Okay, 5 minutes. And you're like, wow, at least I get more time. Your first attempt at solving this will probably be closer to an hour. Okay? So you need to practice. When we go through and look at it, there's 1, 2, 3, 4. We might say, well, 4 peaks. I would argue 4 peaks is a bad word to use. Why? There's a lot more than 4 peaks, so I would actually call this 4 groups or attempt to call it groups. You might still hear me call it peaks. That's just how I was trained. These are 4 groups of hydrogens, or 4 groups of peaks, which means we have 4 unique hydrogens. Okay? If we look at the range, chemical shift, These are all under 2. These are all probably alkane type. This one's over that, which means it is, what'd you say?
Everything else.
Everything else. Okay, you might be, well, that includes a lot of things. That's not very helpful. Yeah, I know. Okay, there's this massive zone within HNMR where a lot of stuff happens. And if you look up tables in your textbook, they'll be like, oh, well, at this value, you have a chlorine. At this value, you have a bromine. And yes, it is perfectly valid. But then you'll go through and say, well, that means I have a chlorine. And yet when you look at the mass spec, your mass spec won't say you have a chlorine. And now all of a sudden you're saying you do have one. Don't analyze that area. Too much crap happens there. It's effectively the fingerprint region of the IR. Right? So don't overanalyze it. So we look at the ranges first. Then where do we go? We could look at the integration. This one's a bit annoying. The ACS is improving a little bit and is actually giving you integration information. I screwed up and didn't give it to you here. Okay, but what we can tell is that this set of peaks is a lot taller than this one and this one, which means that taller one has more hydrogens. Okay. The red ones likely have a little bit less, but not quite as much, and that green one has the least. What would be the least amount of hydrogens I could get? Rhymes with fun, like OChem. 1. Having more would be 2 hydrogens. Having more, 3 hydrogens. We now have an idea of how many hydrogens are in that signal. So when we said 4 unique hydrogens, that doesn't mean 4 hydrogens. That means unique hydrogens. Okay? Chemically distinct hydrogens. All 3 of these hydrogens are chemically identical to each other. I can't tell a difference between them. Okay? After that, we can throw in the next big old caveat and nastiness that everybody likes jumping straight to because there's so much information there, but you oftentimes screw it up. It is the most difficult part to deal with. So don't start there. Do everything else we talked about first. How many hydrogens? What are their chemical shifts? What are their chemical environments? How many hydrogens? Oh God, I have to analyze it. Then look in at the number of peaks within an individual signal. Right? Without belaboring the point more than I have already done so, 3 peaks means 2 hydrogen neighbors. The next one has 1, 2, 3, 4, 5, 6 peaks, which means 5 hydrogen neighbors. The next one has only 1 peak, which means 0 hydrogen neighbors. The last one has 3 peaks, which means 2 hydrogen neighbors. All of that magically gets turned into a structure. What the F? Yeah. In 2 weeks, you can do that. Okay? With practice. So you need to be doing that practice. Okay? Do we need more practice? Tough. The stereoisomers. We have to go back and finish chapter 5. Okay? So in chapter 5, before we do that, 15 and 16 are spectroscopy chapters. You should be reading the textbook, getting a feel for what's going on with that, the kind of underlying theory. We will do the theory on those very fast. Okay? The actual solving process is those videos I've told you to watch. Okay? And they will take time. There's lots of information there. At that stage, you now need to be working on practice. Okay? Admittedly, I haven't gotten up chapter 16 yet. I'll try and get that up later today if I can. If not, it'll be up by Friday, no later than Friday. Okay? That spectroscopy packet is going to be your best friend for how to solve. Do you want to read something that's shorter than 2 chapters worth of material? Read the 10-page spectroscopy background file that I typed up and wrote for you. Okay? You're like, 10 pages. Quit your whine, and it's not 40. Okay? It's been pruned down significantly to just get at the answers. Okay? So, chapter 5. What we're really focused on in chapter 5 is dealing with symmetry. Right? And we run in this concept of stereoisomers, and it's hinging on asymmetry. So the easiest category that we can label, we've actually already done. We've done this with our, not our chairs, what are those? Pi bonds. Those pi bonds have asymmetry to them because I can't overlap them. They're non-superimposable. Okay? If we draw out kind of the bulk chain, we have kind of a stair step versus an umbrella. Right? So that asymmetry means that they have to have a different kind of representation or a different name to represent their relationship. The name we use is our geometric isomers. Okay? Alkenes show geometric isomerism. Rings are not a good idea to reference geometric isomerization on. What the referencing for the rings is actually talking about the cis-trans concept. Okay, so we can reference our rings as cis and trans, just like we can with our pi bonds. Okay, and that's what that's trying to hint at. If we move to an sp3 carbon, now that asymmetry becomes a little bit more difficult to process. If we take a look at that top example, if I take a mirror and reflect the image on the left through the mirror, I would get the structure on the right, yes? Okay. Those are now mirror images of each other. Are they superimposable on each other? Okay. If we just take those structures and slide them across on top of each other, sure, the green one aligns, but then where are the red ones? They'd be out here, and the red one would be out there, and where's the blue one? Over there, when we superimpose across. And you'd be like, well, those don't superimpose, except you can rotate the structure. And when we rotate the structure, because I can't tell a difference between those red atoms, they're both labeled 3s, what happens? They are superimposable. Okay? And this is where OChem again becomes challenging. And I don't think we did it in class, maybe we did. The best way to kind of represent this is that if you attempted to draw me right now, you would probably show eyeballs on my face, because you can see eyeballs staring at you. Okay? And you could say, that's Mike. You can put Mike underneath it, or some other weird string of letters that you want to scream about. Okay? If I then turn around, your drawing had better change because you can't see my eyeballs. Okay? Or that would be a really weird person, and you'd probably freak out. Okay? But the name still changes the same, or still stays the same. The same thing is happening with our two-dimensional drawings of organic molecules. Okay? We have to acknowledge that they are three-dimensional things, and we have to see those spaces and those orientations. Sometimes it's easier than others. With tetrahedral carbons, it becomes very difficult. If we look at the next example, we have 1, 2, 3, and 4. If we go through and do the mirror plane again, or the mirror image, reflects across, we have the mirror image. Are those two structures superimposable? No. Remember, we directly slide across, they don't overlap. Okay? If we rotate it so that the 2 can then be on the left-hand side of the structure, what happens to 3? If 3 is coming out, and I take the 2, there's 2, my index finger, there's 3, and I rotate it so it's on the left-hand side. Where's 3 now? It's going away. Where's the 3 over here? It's going towards. So it wouldn't superimpose anymore. This can be exceptionally difficult to see on paper. This is why model kits come in handy. Okay? What this introduces is a line of asymmetry within the molecule, and we can reference that asymmetry, and we don't need to have the discussion about the use of a, non, and all that fun stuff. We introduce a chiral center. Okay? That chiral center is where the asymmetry is located. so that if I look at the mirror image, it is non-superimposable, and the non-superimposability all comes back to that chiral center. The easiest thing for you to go through to do to find those chiral centers or those chiral atoms is to look for an atom that has 4 different things connected to it. What atom do you think you would find with 4 different things connected to it? Carbon, because carbon has 4 bonds in its neutral state. Are there other atoms that can have 4 different things? Yes, which means other atoms can also be chiral atoms. Okay? It just happens that most commonly we encounter carbon. Does it have to be a carbon atom to be chiral? No. Okay, and the easiest example, staring in front of your hand. Your hand is chiral. It doesn't have 4 different things connected to it. It's non-superimposable on its mirror image. So your definition of chiral is that. Non-superimposable on the mirror image. That's it. For organic structures, it is easiest to identify a chiral atom or a chiral center instead of trying to draw the mirror image and attempting to superimpose it. Okay? Planes of symmetry. Achiral molecules will always have a plane of symmetry. That plane of symmetry can sometimes be obvious. Some people are like, oh yeah, I totally see it. And to you, I usually hate you, because I had a very hard time finding internal mirror planes. Okay? But if a molecule is achiral, there is an internal mirror plane. If we take a look at this molecule, the internal mirror plane splits the chlorine and the bromine in half. Okay? And the hydrogens reflect across. Okay? So we have an internal mirror plane. If we turn that structure sideways, okay, what we might draw would be something along these lines. Okay? It'd be like, well, I don't see a mirror plane. Okay? Even if I draw on the hydrogens, we may not actually see that mirror plane, because the mirror plane is not necessarily easy to see in our other orientations of the molecule. Sometimes it's obvious, sometimes it's not. Okay? So I would stress less about finding an internal mirror plane, even though the textbook is like, oh, this is awesome. If you find it, it's great. If you find it. If you spend all that time trying to find the internal mirror plane, you're slowing yourself down. How do I know that first one is going to be achiral?
Doesn't have the chiral center.
It doesn't have a chiral atom. To have a chiral atom, I have to have something with 4 distinguishable groups. I can tell a difference between the bromine and the chlorine, but the hydrogens are identical. I can't tell a difference between them, which means I only have 3 different things attached. That's an achiral molecule. There's no looking for an internal mirror plane. I can look quicker for that chiral atom. All right? If we move over to the other one, we've changed one of those hydrogens into a different atom. Now we have 4 distinguishable groups. There's not going to be an internal mirror plane. Okay? So chiral atoms, no internal mirror plane. Achiral atoms, internal mirror planes. Pentane. Chiral or achiral? Achiral. There's not 4 different things connected. Where's the internal mirror plane?
The C1, 2, 3, C3.
Damn it.
No. It should be the center.
No, that's a perfect internal mirror plane.
The other one in the mirror, basically.
That's the one I was attempting to do. So if we throw that in there.
Yeah.
Then you have to shift it.
Okay, now where's the internal mirror plane?
The line of paper, basically.
It's literally the line of the paper. Okay, now I have an internal mirror plane. Okay, the line of the paper isn't obvious. And if you're going, oh my God, this hurts my head, welcome to the club. Okay? And that's not easy to see those. That's why I would argue you should just go through and be like, are there 4 distinguishable groups on any individual carbon? No? It's achiral. I don't have to worry about an internal mirror plane.
If there's only one?
If there is a chiral atom, the molecule has the potential to be chiral. Okay? So we'll look at an example here. What do we think? Achiral or chiral? So for the people saying chiral and achiral, getting both answers, you're right. One of these is chiral, one of them is achiral.
Chiral, then achiral.
Yeah.
Yes.
Top one is chiral, the bottom one is achiral. Okay? That becomes tricky because if we're thinking about these structures in 3 dimensions, we should be thinking about wedges and dashes and all that stuff. Do you see a wedge and a dash? No. It looks like it's just straight up. Can that possibly be going just straight up?
No.
No. It can't physically be going just straight up and those bonds being all in the same plane. We just decided to not show the wedge and the dash. Can we do that? Yeah, it's rude. Okay? But we need to acknowledge that that is a chiral atom, which makes that molecule chiral. The bottom one, we don't have a chiral atom. That molecule becomes achiral. Yes?
So like in future questions, so we just assume that it is coming at us, I guess? Or...
So a good question would be, well, what is it? Is that bromine coming at you or going away from you?
There's no way to tell.
There's no way to tell with how this is drawn. So if this was given to you and you were asked to predict something about the reactivity, am I specifying the chirality of the molecule? No, which means do you need to specify the chirality of your answer? No. Okay. What this is saying in a question is that I'm actually giving you a compound or a mixture of both of these things. Okay, both of those things are coming together in the single sample I'm giving you.
So you're going to have your wedge when you refer to...
Yeah. So if I want you to be concerned about chirality in your answer, I need to be more specific about it. Okay? And since you brought it up, I was going to go there anyway, but I'm going to blame you just for it. Blue box. In the blue box, chiral or achiral?
Achiral.
It's achiral.
Don't
I referenced the blue box, not the individual molecules within it. Okay? For those of you being like, what? Yes. Okay? Here's something that would make it a little bit more apparent. The red star, chiral or achiral? Chiral. The blue star, chiral or achiral? Chiral, the molecule. Achiral. There's an internal mirror plane. So to Domla's question earlier, if you have a chiral atom, is the molecule chiral? No. If you have one chiral atom, yes. But as soon as you add multiple chiral atoms, they could potentially counteract each other. Okay? The blue box becomes a really tricky one to deal with as far as that mixture being achiral. The individual components are chiral, but the individual or the mixture itself is achiral because it has both components in it. Okay? That becomes more apparent when we actually talk about the physical properties of these individual molecules and how we would see those physical properties. Okay? So what this is bringing in is officially 3 new definitions: enantiomers, diastereomers, and meso compounds. Enantiomers are structures that are non-superimposable on their mirror image, or are mirror images. Okay, so enantiomers are chiral. Okay? Diastereomers is a relationship between two structures that are non-superimposable as well, but are not mirror images. That one becomes a harder one to work with and define, which is why the textbook talks about them second. Enantiomers have one or more chiral atoms. When you only have one, it's really straightforward because then it's chiral. When you move to diastereomers, you have two or more chiral atoms. What happens when we move to meso? A meso compound is superimposable on its mirror image. Well, if it's superimposable, wouldn't we call it achiral or identical? It would be the exact same compound. But we're adding a layer of information because it also has two or more chiral atoms. It has that added little stab in the back of chirality internally within the molecule, but that internal situation cancels out. The blue star, chiral or achiral? Purple star, chiral. Is there an internal mirror plane? Yes. If I attempted to draw the mirror image of this structure, it would be identical. So it would be superimposable on the mirror image. This red structure is known as a meso compound. What happens? Oh, do I really want to stepwise back that one? Yeah, that wasn't too bad. What is the relationship between the red structure and the black structure? Right? Certainly not meso anymore because they're not superimposable. Okay? We do have chiral atoms in both, so it could be an enantiomer. It could also be a diastereomer. For them to be enantiomers, what must be true? These must be mirror images of each other. Are they mirror images of each other? No. Since they're not mirror images, the relationship between those two structures is diastereomers. Okay? So what we're doing is going back to that big old chart in the sky of all of these things and adding on your diastereomers, your enantiomers, and your meso compounds. So you can easily see questions where it's, here's two structures, tell me the relationship, and I list out any possible combination of any of those systems. Okay? If you understand the relationship of those definitions and ultimately the flow chart, you should be able to identify those definitions. Okay? What can make it more challenging? Think about exam 1. I can draw the structures as chairs. I can draw the structures as Newman projections. I could draw one as a Newman projection and one as line angle. Okay? All of those possible permutations are now things that you have to be able to see those relationships to identify the relationship between the structures. Okay? Does it suck? Absolutely. Okay? But that's what you have to be able to go through and process. Okay? Kind of makes sense? Okay, identify their relationships. Give you an idea of how many relationships. We've got 1, 2, 3, 4, 5, 6 relationships. 5 minutes. So if we go through and take a look at these. So number 1, I overlaid some stuff in blue. It's kind of a mess. It is really kind of messy. Unfortunately, we're just going to have to deal with it. So the first question was looking at the left side. So a couple people started looking at just comparing the top and the bottom. And so they were like, well, I know enantiomers are mirror images, so I'm going to draw a mirror image. It's an awesome first place to start. So they drew the mirror image of the top structure. And so that's what I drew there. Kind of crammed it in there. Everybody see that that is indeed a mirror image of the structure. And they took that image and then they tried to overlay it on the bottom one. So you took this and just went, shoosh. That didn't fit. The double bond's on the wrong hand side. Wrong? Yeah, it's good enough. Okay. is my right hand a mirror image currently of my left hand?
Yes.
Yes? Is there a mirror plane? If I put a mirror right here,
No.
no, oh wow, that wouldn't work, right? Is my left hand still a mirror of my right?
Yes, it's still is.
Yes. You have to flip the structure around. If we take that mirror image and we just turn that over, what happens? We would draw this structure. This structure happens to be
That's the entry.
superimposable with this one. Right? Which means these two are identical. These two are mirror images. Which means this one is identical to this one, which means enantiomers. On the left-hand side, the relationship of those structures is enantiomers. Those are being like, oh my God, that is really difficult to deal with. This is why I hate dealing with this chapter, because that's how I had to do every single question ever. Okay? And yes, that is challenging to deal with. Okay, so let's see if we can come up with a potential kind of cheat, if you will, on this. I would hesitate to call it a cheat because really it's just coming from experience. If I take a look at my left and right hand, right? My thumb is on which side of my right hand?
Our right. Your left.
For you, just tell me you.
Right.
Right.
Side.
Okay, if I look at my mirror image, my left hand, where's my thumb?
Left.
On the left-hand side of the structure. Okay? So it's flipping. Right? If we go up and identify our chiral atoms in that top structure, you should be able to identify that spot and that spot. What happens to the OH? Let's call it the red OH. When I go down. It was dashed, and what happens to it in the bottom structure? It's wedged, which means it flipped. It's a mirror image. If I do a mirror plane through the middle of the structure, it flipped across the mirror. So that one spot is a mirror image. What happened to the other position? It also mirrored, which then means they are mirror images of each other. We have enantiomers. Okay? So let's take a look at the top relationship. What happened to the red dot? It flipped. That means it's mirrors. It must be enantiomers. Look at the other chiral atom. What happened to the other chiral atom? It stayed the same. Okay? When we mirror the hands, everything mirrors. It's not like just the thumb trades sides. The pinky also trades sides too. Okay? So everything must flip. Not everything exchanged. Which means they're not mirror images. Are they superimposable on each other? No, which means the relationship is diastereomers. Interestingly enough, everybody has pronounced that correct so far in this class. Usually people butcher that pretty badly, and you're more than welcome to call it disasteromer. That's okay. It's officially wrong. It is diastereomer. Okay? As you might tell by the color coding here, what's the red relationship through on this angle? Also diastereomer. Okay? Notice what's happening is I'm not flipping the top one, I'm flipping the other one. Okay? The green one is, of course, a new relationship. That new relationship is not inherently obvious. Okay? Usually people end up calling this extra carbon as an extra carbon and go, oh my God, an extra carbon must mean that it's different from all the other ones. Is it actually extra? No, we actually took the methyl group off and we just changed the location. We changed the connectivity, which means constitutional isomers. Okay? We're still trying to mirror the image here. You might be like, well, isn't that kind of cold? Yeah, it is kind of cold. Okay, we're mirroring it so that we make you think nothing happened out here. You got to watch out for the whole structure. So we have constitutional isomers in green. Kind of makes sense? Okay. So, multiple stereocenters. Okay, in this structure, we have two potential stereocenters. We could get asked the question, how many possible stereoisomers are there? Okay, and the textbook goes through and gives a neat little formula. It's 2 to the n. What is n? The letter after m. The number of stereocenters. How many stereocenters? Laughing was way excessive on that, guys, by the way. That was a horrible joke. There's 2 stereocenters, which means 4. I should be able to draw 4 different stereoisomers. Okay?
No.
I can draw 3. Notice there's a little minus there. -1 for an internal mirror plane. Is there an internal mirror plane in this structure? Yes. Because of that internal mirror plane, I would have to subtract 1 from the total. What do my 4 look like? Did I draw all these already? No. Damn it. Really? Fine. Yeah, you gotta check. Recommendation for trying to draw all your stereoisomers. Okay. Number 1, don't draw all of those out. I'm doing that because I know the answer is 4. I'm going to pick that red carbon. That chlorine can be wedged or dashed. The blue carbon. Whoops. The blue carbon could be wedged or dashed. It's now just a game of filling in the pieces. Everybody see? Okay. So remember, all I'm trying to do is show all possible combinations. Okay? It says to subtract 1 for the mirror plane. To the end just says this is all your possible combinations. Why do I have to subtract 1? Take a look at this structure here. If I take that structure, they're both dashed, right? Pick it up and I flip it over. Okay? For those of you being really observant, yes, I know the colors don't match, but I added the colors, so that doesn't count. Okay? Those 2 structures would be superimposable. These are identical structures, which means I need to cross one of them out. Okay? So I end up with 3 stereoisomers. Kind of make sense? Is that a no? I guess that's fine. I just need to know. I'm going to assume silence meant we're okay. Stereoisomers. How many stereoisomers for that compound? Oh my God, that's impossible. Breathe. Rhymes with door. You're like 4. We even got a confident none. Take a look. A confident none. That's kind of funny. Sorry. I don't know why that was funny, but it is. The red dot. Is that a stereocenter? Yes, that has 4 different things. So that is a chiral atom. Blue dot. Yes. Also a stereocenter. So I have 2 stereocenters. So 2 to the n gets me 4. Notice, because I'm doing them both at the same time, red and blue, I get purple. You're welcome. Is there an internal mirror plane? No, so I don't subtract anything. There's 4 stereoisomers. Okay? Is there a shortcut to that? Because I heard a lot of people like sucking breath when they saw that and go, oh my God, I got to look really hard. Where do stereoisomers or where do chiral atoms show up? What kind of an atom? Carbon, number 1, and sp3 hybridized, or tetrahedral carbons. You mean the stuff that we talked about in Unit 1, being able to recognize relatively quickly? Yes, because now you can recognize it relatively quickly, and you can jump all over those carbons and ignore pretty much the rest of the structure. So now when we go through to answer it, is that a little bit easier to see that there's 4 stereoisomers? Yeah. Okay. Selective vision. It is a skill that you need in OChem. Okay. You have to ignore that kind of secondary stuff. Okay. It requires practice to learn what is secondary, but you have to do it. Okay. Or struggle through with a lot of those. So, is the molecule chiral by marking all the stereocenters and determine the possible stereoisomers? minute. It's not too bad, right? How many stereocenters in the first structure? 1. Right there. There's our stereocenter, where that CH3 is. 1 stereocenter, 2 to the n is 2. Not to give anything away, but you can read the answers I've written in underneath. How many stereocenters in that second structure? None. But isn't there a wedge? I don't care. Completely irrelevant. Okay?
There's 2 things that are the same.
If we go through and evaluate, are there 4 distinguishable groups? We get the chlorine, we would get a carbon and a carbon. I can't tell a difference between those 2 carbons, so I could continue to move through the structure to try and find that difference, and I would end up doubling up on myself. Meaning I can't tell a difference between those carbons, which means there are only 3 distinguishable groups in that structure, not 4, which means not chiral, which means there are no stereoisomers for that compound. Okay? That is tricky. We tend to zero in and hyper-focus on things that we recognize. With Chapter 5, one of those hyper-focus things tends to be wedges and dashes, because we're thinking that's a signal that we're looking for chiral atoms. Just because there's a wedge or a dash does not make it chiral. You have to think a little bit further and look for those 4 distinguishable groups. The last one, that one is a chiral atom, that blue one. But can I tell a difference between those 2 carbons? Aren't they both CH2s?
They're the same.
We move to the next position. Those are different. If those 2 positions are different, what does that mean about the blue carbons I've circled? They're also different, which means that is indeed a chiral atom. Also chiral, also chiral. So there's 3 chiral atoms. If I did the math right, I think I did. 2 to the n, or n is 3. 2 to the third is 8. And there's our chiral atoms for that. Okay, or our stereoisomers. Kind of makes sense? This pattern is a pretty nice lead-in of going through and looking for 4 distinguishable groups. Okay? It works out really well both with spectroscopy and Chapter C, or the nomenclature part, of looking at these chiral atoms. Okay? And I know we're kind of tight on time. If we take a look, this is thalidomide, the anti-nausea drug. This is thalidomide, the making kids not have arms. Okay? All it comes down to is that stereocenter changing. They are mirror images of each other. Okay? This means I had better have a naming system that allows me to differentiate that. Okay? Because I just take thalidomide. They're like, well, which one am I taking? Like, am I not going to get sick, or am I going to lose my arms? That's kind of a big deal. Okay? So we need to have a naming system that incorporates that. That naming system comes back to identifying those 4 different groups and assigning priorities to them. That system is known as the Cahn-Ingold Prelog rules. That system applies for our chiral atoms, R and S, and also cis and trans. Okay? These are our rules for assigning priorities. You identify your chiral atom or your potential cis-trans location. You assign priorities to each substituent based on atomic mass. And that's where it gets tricky. It is always atomic mass. You go through and you assign. What if you find that there's no difference? We came to 2 CH2s. What do? We move to the next atom in the sequence, and we evaluate again. You move to the next atom in the sequence, and you evaluate again. And the next atom and the next atom. If you can't find a difference, it wasn't chiral. Okay? If you find a difference, that means you have different priorities. You have to assign that priority correctly all the way back up. Okay? Where it becomes tricky is D, is if you see multi-bonds, alkenes, alkynes, carbonyls, each pi bond gets treated as a new sigma bond. Okay? Which sounds really weird. Don't stress about it right now because we don't have time to talk about that quite yet. We'll start with examples Monday. Okay? You'll also hear it sometimes referred to as a ghost bond. Yeah, ghosts. You'll then orient the molecule so that the lowest priority, number 4, is aimed away from you. Once that is done, what you'll be looking at is effectively a Newman projection, and you now just connect a little circle from 1 to 2 to 3. If when you connect those, you're moving in the clockwise direction, that chiral atom is assigned R. If when you connect them, you're moving in the counterclockwise direction, it's S. Where's the added complication? Which way is my hand turning? Your perspective. Really? Depending on which way you're looking at the molecule, your assignment changes. This is why you must have the lowest priority aimed away from you. You must. Okay? If you check the internet, and feel free to pack up, if you check the internet, people will come up with different ways. Oh, if it's this, you just do this. If it's this, I've never consistently gotten any method to work other than doing this. This is tedious and painfully slow. If you can find something to consistently work, by all means, go ahead and use it. I won't, because I don't trust it. Okay? The problem with it is your answer is either R or S, which means when you do the process, half the time you're right, half the time you're wrong. And I think that's where the issue with these other methods comes out, is half the time they're right, and it happens to be the time that they're showing you how to do it. And the half the time that they're wrong is when you're taking the test. Okay? So just be aware of that. I don't recommend any kind of shortcuts with assigning R and S. It has to go out in this fashion. We'll start with the example.